In the last lecture, we saw how difficult it is to come up with a suitable definition for aging. What we'll do today is to expand on that idea, and I'll show you examples how to actually measure the aging process, how to measure aging itself. How then do we truly measure aging? One approach would be to take stock of all phenotypic manifestations of the aging process to establish a comprehensive aging phenotype. However, as we have seen, this is highly species-specific and even within any given species, specific for various subpopulations. For example, wrinkled skin is a typical human aging phenotype, but not for other fur-covered mammals. And even within humans, fair-skinned population groups experience a greater rate of skin aging than darker-skinned ones. We will talk about human aging phenotypes in a later module, but for now, that already shows the difficulties in comprehensive phenotype estimations. Given the wide range of these phenotypes and the variability between species and within population, such an approach is therefore highly situational and has to be very, very carefully applied. Another way to determine whether a population is undergoing aging and its rate of aging is to measure age at the time of death. This method is universally applicable and, more importantly, unbiased. Such data is displayed in a survivorship curve, with 100% of a population alive at the beginning of the curve and 0% alive once the last surviving individual has died. Such a survivorship curve, moreover, contains information about the median lifespan, the point where 50% of the population has died, or the age where 50% of the population has died, and its maximum lifespan. Maximum lifespan, it should be noted here, is not the lifespan of the last surviving member of a population. And that can't be the definition of maximum lifespan because there's this huge variability between individuals in the aging process. Instead, it is defined as the median lifespan of the longest lived individuals. Usually, that's the longest 10% or the longest lived 5% of the population. Using these definitions, species-specific maximal lifespan can then easily be determined and can range from a few hours, a few years, to even several hundred years, like the ocean quahog that we talked about last time. Species-specific lifespan was one of the earliest measures that was used to develop the first theories of the aging process, and we will talk about these theories in the next module. The other thing that you can do with such a survivorship curve is then to easily convert them into the Gompertz mortality rate curves. This then provides additional information on the intrinsic rate of aging, which is represented by the slope of the Gompertz curve, and the presence of any extrinsic hazards, which is represented by the y-intercept. If an extrinsic hazard exists in a population, such as disease, high levels of predation, lots of accidents, that leads to high mortalities. And therefore, a survivorship curve would look almost like a straight line. And the Gompertz curve, in turn, would look like a straight line that is parallel to the x-axis, with high extrinsic mortality on the y-intercept and almost no increase in the age-specific mortality. In the absence of an extrinsic hazard, the survivorship curve then will look sigmoidal, almost like a rectangle when the extrinsic hazard is really, really low. This is called the rectangularization of the survivorship curve, and is something of a holy grail in the aging research community. You're trying to exclude any kind of external hazard and really trying to investigate only the intrinsic aging process, and is more likely to occur under artificial laboratory conditions. The Gompertz curve then will look like a regular line, and you'll see that age-specific increase in the mortality rate, and the y-intercept is very low because you have that low extrinsic hazard. Achieving this rectangularization of the survivorship curve in the laboratory context would not only mean that extrinsic factors have successfully been eliminated, but also that the stochastic individual nature of the aging process was largely a non-factor. The corresponding Gompertz curve will then be a line defined by a similar linear equation, y equals mx plus n, with n, the y-intercept, representing the external hazard, and the slope m represents the actual rate of aging. Using these two curves, the Gompertz mortality rate curves and the survivorship curves, an investigator can now quickly determine whether any intervention or different populations has increased longevity, that is, increased maximum and medium lifespans. And you could also make predictions on why that longevity is increased. Is the hazard function altered, or is the actual intrinsic rate of aging altered? For example, elimination of diseases, which is an extrinsic hazard, would result in a lowering of the y-intercept, but not necessarily in a change of the slope, the rate of aging. The great gains in human life expectancy that we observed in the late 19th and 20th century were largely due to advances in medicine and nutrition, and that reduces disease-dependent cases of mortality rather than the actual intrinsic rate of mortality. So we were able to lower the hazard function, and that increased our lifespan. But our aging process is still going on. A more real-life example is shown here, comparing the survivorship curves and mortality rates of Japanese women, either women that were born early in the 20th century or late in the 20th century. These survivorship curves look almost perfectly sigmoidal, especially for the later years, the one from 2007. They look slightly more than a rectangle than the earlier ones. Especially you'll see that little dip here in the first 15 years. That represents an extrinsic hazard, early childhood mortality, especially very close to World War II. This dip is also observable in the mortality rate curves when you convert the survivorship curves into Gompertz mortality rate curves. Age-specific mortality is very high in the first few years after birth, especially when we're looking at the early curve around 1947, right after World War II, where bad levels of nutrition existed in Japan and healthcare was not what it is now. So advances in these nutrition and healthcare reduced childhood mortality rates in the intervening years between 1947 and 2007, leading to overall lower mortality rates, but not quite limiting childhood mortality. That means the extrinsic hazard has been significantly reduced, but not quite eliminated. So we still see that raise in mortality rates very early on. But longevity may also be extended because the rate of aging was slowed down, which would be apparent in an altered slope of the Gompert curve, which would represent a truly delayed or slowed aging phenotypes. Sometimes in some experiments, one can observe both a slope change and a y-intercept change. So in that case, you would lower mortality rate and the rate of aging itself. Many of the manipulations that we will talk about during this class displayed an altered slope and were then, therefore, actually slowing the aging process itself. For example, if you look at panel B of this figure, you'll see Gompertz mortality rate curves for wild-type mice and some genetically modified mice that are long-lived. These so-called lit mice have a defect in growth hormone, are of a dwarf phenotype, and in fact live 25% longer than wild-type mice. However, the slope of these two curves is almost identical, with a lit curve merely shifted to the right, which then, of course, leads to a change in the y-intercept. That means that the actual rate of aging between these two mice may be similar, and that the increased longevity observed in these long-lived lit mice is merely due to the lowering of the extrinsic hazard function, which is, of course, the y-intercept. If you look at panel A, you'll see Gompert curves for wild-type and captive baboon populations. Here you see a change in the y-intercept. If you extrapolate both of these curves all the way to the y-intercept, that means these curves are shifted up and down from each other. So the hazard function is altered. But also what you see is a change in the slope of these curves. That means you also see a lowered mortality rate. In other words, whatever this intervention is that was used here, it slows down the aging process itself. And we will talk about interventions that can do that, especially in the final module of this course.